All right, hello and welcome. I'm Edward LeBeau again here with our lecture series on crystalline silicon solar cells. Let's go ahead and dive in. So today we're going to talk about characterization. Let's just outline that and then we'll tell you what characterization really means. So first things first, we'll explain why we need to characterize solar cells. Then we'll look into IV testing, Suns Voc test, lifetime tester, quantum efficiency, electro-luminescence, and photoluminescence. And those are all just different characterization methods that we have, different tools for characterization really. So really, real quick, what is characterization? Characterization is just defining different key metrics on your cell. And why do we need it? Because we want to understand exactly what's going on in the cell, what it's doing well, what it's doing poorly, how to improve. And there's many ways to explain different effects. There's a delicate balancing act going on with solar cells, and it has many factors, and we want to understand them also. At the end of a well-characterized cell, we want to know the minority carrier lifetime, surface recombination velocity, saturation current, implied VOC, the fill factor, and then the fill factor without the series resistance, ideality factors, iron concentration, and many other things like diffusion density, doping density, tons of information we want to have. And that's so that we know what's going wrong, what's going well, and how do we improve. And that's the big thing is you'd hope we'd be improving our process as time goes on. So first things first, we'll talk about IV curve. So basically an IV curve, we've mentioned it before, is first you short the cell, flash a light, measure your short circuit current, then you open the cell, flash a light, measure your open circuit voltage, and then you do everything in between. And what comes off that, the efficiency, right, the very important metric, efficiency, the open circuit voltage, the short circuit current, and the fill factor. So those are all important metrics that come off of the IV curve. The next thing we have is the Suns Voc, remember, open circuit voltage. So basically what you do is you measure the open circuit voltage while you vary the light intensity. So you flash different intensities of light and then see what the open circuit voltage is on the cell. So if you look at this, though, as your light intensity goes up, at some point your voltage doesn't also increase. And that's largely many different reasons, but a big piece of that is technically the backside of your solar cell is a diode. So if you have a large enough voltage, it'll short across it. So basically, as your intensity goes up at a certain point, the voltage across the back contact becomes high enough to turn on that diode. And then we also have a lifetime tester. So basically what a lifetime tester is there's a flash of light, and then you monitor the conductivity of the wafer using a coil. So you put your wafer down, and underneath it's this coil. You flash a light that excites all these electrons, they're moving around, and that is inducing field on the coil underneath it. So there's a couple different ways to get lifetime out of the conductivity. And if you look at those two equations, those are both very useful equations. So there's really three ways to do it, but the main one to do it is a generalized analysis. And that's, if you look at that equation, it's basically your lifetime is the change in your carrier density over your generation minus the rate of change of your carrier density with respect to time. And if you look at the plot there, you have your illumination intensity on the left, your time, and your photoconductivity on the right. So the red is the signal coming off the cell, and the blue is the signal from the light. So if you look at it right when the light flashes, you have a high conductivity. So you just excited all these electrons. And then as time goes on, they recombine, and the conductivity tapers off because you have less electrons in the conduction band. Less electrons in the conduction band, more resistance. So there's a couple issues with lifetime testing. Two are there's some background noise in the transient response. You can't really get rid of that. And then also on the lifetime test, there's no trapping correction. So real quick, what is trapping? Trapping is when an electron jumps to one of those discrete energy levels that isn't the band from the silicon solar cell. So you jump to a discrete energy level that isn't a useful energy level. It's excited, it's conductive, so it skews your lifetime slightly. But there isn't much of a correction for that for a lifetime tester. Now, the next characterization method we'll talk about is quantum efficiency. So basically quantum efficiency is the ratio of I shine 10 photons, hit my cell, and how many electrons do I get out as I vary the wavelength is basically what we're doing. And ideally, for every photon that hits, you get at least one electron come out. Obviously, that's not the case. So if you look at this plot, some interesting things to note is blue light. If it hits the solar cell, it doesn't have 100%, and that's largely from front surface recombination. Then you have just a general drop, and that's largely from reflection and diffusion length and things like that. And then as you hit red, you begin to figure out how well passivated is my back surface. And then if you realize as you go past red, you're beginning to enter wavelengths that are too low of energy to jump the band gap. So an ideal quantum efficiency would just be 100% electron, 100% of photons create at least one electron, and then at some point you're too low of energy for the band gap and it just falls right off. Obviously, we don't live in an ideal world, so there's lots of room for improvement. The next characterization method we'll talk about is electroluminescence. So what is electroluminescence? Just you treat your solar cell like a diode, like a light-emitting diode, because it technically is. So we apply a voltage across the cell that excites electrons, and then they de-excite and light comes out, right? Because we're not collecting the excited electrons. And you have a camera over it, and you just watch the electrons come out. And you figure out some useful things there. Obviously, if you look at that picture, your bus bars aren't going to produce any light. That's not where the electrons are de-exciting. But if you look at it, you can see your print problems, right? That little dark spot with print problem written over it is chances are that's where some fingers didn't get printed quite correctly, so there's no voltage there, no applied voltage there because the fingers aren't quite right. And then you can also see some other interesting things with like micro cracks and fractures and things like that as you see that cleave right across the wafer. So you figure out some interesting things about how well the wafers were handled in the process from electroluminescence. And then another similar process is photoluminescence. So rather than using electrical excitation in electroluminescence, you use photo excitation. So you shine a light on your wafer. All the electrons get excited, just like when you applied a voltage. And the electrons de-excite, and obviously not de-exciting, just like before. Light comes out. The interesting thing with photoluminescence is you can do it at any stage in the process. You don't need contacts or anything. Like electroluminescence, you can only do it at the very end after contacts are on the wafer. So this can be useful to do each step of the way look at things. And obviously, if anytime there's dark spots, that points to an issue. Largely, it's a contamination issue, things like that. So yeah, that's our lecture on characterization. Hopefully you enjoyed yourself, and I hope you've been enjoying this lecture series. It's beginning to wind down.